We are now on lesson 4.3, and lesson 4.3 is called Implicit Differentiation. Okay, and the first thing I want to do, Carrie, is I want to attack the word implicit.
Okay.
I want you to understand exactly what I mean when I use the word implicit. So let's first look at the definition of implicit. So here's the definition. Implicit means implied, though not plainly expressed. Implied, though not plainly expressed. And there's a biblical idea here. We can actually go to the Bible and we can find an example of implicit. So here's 1 Peter chapter 1, verse 8. Though you have not seen him, you what? Love him. Though you do not now see him, you believe in him and rejoice with joy that is inexpressible and filled with glory. We love Jesus not because we've seen him, but because we have accepted him into our hearts. We have been convicted by the Holy Spirit. We trust that he is our salvation. But we have no physical, I've seen this person. Our trust, our love is implicit. So I'll go back to the definition here real quick. To this definition, our trust in Jesus is implied, though not plainly expressed. We have no physical, touchable hands of Jesus that we can physically touch. Bad timing for the bell, but anyways. But one day we will. But right now, our love for him is implicit. We implicitly love, we implicitly trust, though we don't know what's going to happen in the next few seconds. Right? Okay? Now, take that same idea, and I want you to carry that idea throughout the rest of the lesson. Implicit differentiation means we are going to differentiate equations of y and x without knowing how to express y as a function of x.
Without knowing?
Without knowing how to express y as a function of x. Let me show you what I mean by that. So, here's an example of an equation, x squared y plus y equals 3.
Okay.
Now, even though y is not expressed as a function of x, it is discoverable. Let's write down that word.
Meaning that we can put y equals negative x squared y plus 3?
Yes, you can solve for y.
Yes.
But right now, I'm not going to do that. Right now, I'm just going to say y is a function of x. So that's what the equation there that I've written means. Y is a function of x. It's still the same old y equals some equation using x's. Okay? And using this fact, I'm now going to be able to differentiate this. So let's go ahead and do that. Before I do that, whenever I take the derivative with respect to x of y, I get dy dx, right? And we know that this is the same thing as f prime, right? Even though I'm not going to write it. All right, now let's look at this right here. Okay, 2y times the derivative of what was inside the square, which is y. So I get 2y times dy dx. If I have d dx of y to the nth power, then the nth power has to be dealt with first. So this is n times y to the n minus y. But then the chain rule says now differentiate what was inside the nth power, and that's y. So what is d dx of y?
Y prime.
Y prime, which we'll write as dy dx. This is the same as y prime. So these notations, dy dx, y prime, f prime of x, they're all interchangeable. They all ultimately mean the exact same thing. Okay? So now we can take this equation right here. I'll go ahead and rewrite it. X squared y plus y equals 3. And we can differentiate it. So let's do that. So here's a product, so I have to use the... So first times the derivative of the second, x squared dy dx, plus second times the derivative of the first, 2xy, plus now the derivative of y, dy dx, equals the derivative of a constant, 0. Now I'm going to solve for dy dx. I'm going to subtract 2xy to the other side. So this becomes x squared plus 1 dy dx equals negative 2xy. And so dy dx equals negative 2xy over x squared plus 1. Okay? It isn't. And I want you to know, morning.
Good morning.
I want you to know that we have not invented a new differentiation here. This is the same derivative that we've been doing before. This is still the slope of the tangent line at the point x, but the difference here is that we didn't know y as a function of x. Okay? Now, let's go ahead and solve this equation now for y. So let's do this part. We can factor out a y, right? Correct. And now this right here, this equation that we have, this is called explicit.
Is it alternative with
The homework? Okay. Yep.
alternative with implicit?
This equation is explicit. And all of the differentiation that I've been teaching you so far, David and Carrie, has been explicit differentiation. Let me now show you that if I take the derivative of this, I get the same thing here. Let me show you that I get the same thing. In order to do that, though, I'm going to have to erase this, and so I'm going to have to trust in your notes what you have, Carrie, okay? So let me take y. Yep. And now let's differentiate this using quotient rule. Low d high, so x squared plus 1 times the derivative of the top, which is 0, minus the top times the derivative of the bottom, all over the bottom squared. So I'm just left with negative 6x over x squared plus 1 squared is what I'm left with. Are we okay with that? Okay. Now can you tell me what I got for dy dx the other time? What was it? Was it negative 2xy?
Negative 2xy over x squared plus 1.
Okay. Now let me show you that it's the same. I now know what y is explicitly. It's this. So I'm going to substitute. I'm going to replace the y with this. So this becomes negative 2x over 3 over x squared plus 1 over x squared plus 1. But that's equal to negative 6x over x squared plus 1 over x squared plus 1. And this reciprocates, giving me negative 6x over x squared plus 1 squared. And so the implicit derivative is the exact same result as the explicit derivative. The implicit derivative is the exact same result as the explicit derivative. The only difference, David, was when I did the implicit derivative, I didn't know what y was as a function of x. I just trusted that it was a function of x, and I proceeded from there. Does that make sense? Okay?
Do we have to use implicit if we get the same answer with explicit?
To be honest, implicit in a lot of ways is easier. Yeah, let me show you an example. So let's go right to the textbook and let's go to the homework examples here. So I'm going to open up 4.3. Now, is that always true, Carrie? No, sometimes the explicit derivative is going to be easier. But implicit derivative can be an advantage. And you know what? As odd as this sounds, in the real world, sometimes you don't know what y is as a function of x. You only know the implicit equation holds some model for some real-world situation that you are trying to use. Okay, so we need an example of a case that would be easier. I think that this would be a good example right here, number 12. So number 12 is x cubed minus y cubed equals 6xy. Well, I'm going to write this. I'm going to modify it. I'll just write x cubed minus y cubed equals 6x. Let me modify it just a little bit. So this isn't exactly number 12. Okay? All right.
Sorry to interrupt.
That's all right.
Have you done the most recent Java?
Okay, so now, yes.
Why are we putting in 6x instead of 6xy?
It's going to help me to show you that the implicit derivative would be nicer in this instance. So I reserve the right as the teacher to modify it, basically. Okay, let's find out what y is as a function of x. What would we have to do here, David, to solve for y? Okay, so that means that x cubed would equal 6x plus y cubed. 6x to the other side, so x cubed minus 6x equals y cubed. Cubed root. So the third root of x cubed minus 6x is equal to y. That's exactly right. Now let's differentiate that. Let's find dy dx.
First, you have to use the chain rule.
Right. That's correct. We need the chain rule.
So,
I rewrite this as to the 1/3 power.
so 1/3 times x cubed minus 6x to the 2/3
Correct.
times 3x squared minus 6.
Correct. Now let's rewrite this. This becomes 3x squared minus 6 all over 3 times x cubed minus 6x to the 2/3 power. Not too bad, right? Okay.
Oh, okay.
So we agree that that's the derivative. All right? Let's go back now and let's find the derivative of this guy implicitly. So x cubed minus y cubed equals 6x. Now, the way that it works is we start taking the derivative. So what's the derivative of x cubed? Minus 3y squared by the chain rule dy dx, because y is a function of what? X. So the 3 comes down, so it's 3y squared, but now we have to take the derivative of y with respect to x, so dy dx equals 6. Now we solve for dy dx. So dy dx, negative 3y squared times that, equals 6 minus 3x squared divide by negative 3y squared, and I have dy dx equals 3x squared minus 6 all over 3y squared.
Wait, isn't it 6 minus 3
I divided by a negative 3y squared,
squared?
and so that lets me switch the signs. And my claim is that this implicit derivative is exactly the same as the other derivative we got. Now, a lot of this already looks the same. We still have a 3x squared minus 6 here, right? Over 3. What would I substitute this with? This is y squared. And what did we solve for y? What did we get?
X cubed minus 6x.
X cubed minus 6x to the 1/3 power. So if I put this in, and if I square a 1/3 power, I get a 2/3 power. So this is exactly the same as the derivative that we did before. Okay? Does that make sense?
Yeah.
So implicit differentiation is not a new differentiation.
So which one was implicit? The one that we just did?
The one that we just did.
Is there another one?
Yeah, absolutely. It's not a new differentiation. The only difference is that we do not know y, good morning,
Good morning.
as a function of x explicitly. The only difference is that we do not know y as a function of x explicitly. Okay? All right, let's tackle another one. Here's a really good example of where implicit differentiation is nice. I'm actually going to do 15. 1 over y plus 1 over x equals 1. So 1 over y plus 1 over x equals 1. Now, is it possible for this example anyways, to solve y, to solve for y?
No.
Yes, it is. So we could know what it is explicitly. We could know that, okay? But we're not going to. We're going to proceed. We're going to proceed implicitly, not knowing what the equation is, okay? So what I do is I rewrite this, McKenna, as y to the negative 1
Plus x to the negative 1.
equals 1.
The
And now I take the derivative of this.
Negative y, negative power to the negative 2.
So negative y to the power negative 2,
dy
but dy dx by the chain rule, yes. Plus negative 1 x to the negative 2. Now again, we'd use the chain rule, David, but the derivative of x is 1. So that's why I don't write the times 1 out here. Equals 0. And now I start to solve. Dy dx equals x to the negative 2 over y to the negative 2, but this reciprocates, actually this is a negative y, so this reciprocates to negative y squared over x squared.
Is the next one the x92 as well?
Right. These are both negatives, so what does it mean, x to the negative 2? It means 1 over x squared.
Yeah, but like
One.
up there, like after it says plus negative 1, so isn't that?
Plus negative 1 x to the negative 2.
So isn't x92?
So, no, because I added it over here.
Oh, okay.
Yeah, I added it over, that made it positive, then I divided by a negative. So the result's going to be negative. Okay, now let's take that same 1 over y plus 1 over x equals 1. Let's solve that equation now for y. So what I'm going to do, Carrie, is I'm going to take the equation here and I'm going to multiply by xy. And that gives me x plus y equals xy. Subtract y over here, so x equals xy minus y. Factor out a y, so x minus 1 times y. So I have x over x minus 1 equals y, and now I know y explicitly. As a function of x. So we can differentiate this using the good old chain rule. What would dy, well, chain rule, yes, but quotient rule is what I meant. So what do we do? Yes, low d high. So x minus 1 times 1 minus, not equals, minus high d low all over low low. Well, do you see that this just ends up with negative 1 over x minus 1 squared? All right, well, let's just now go and show that that's exactly the same thing as what we got before. What we got before was dy dx is equal to negative y squared over x squared, right? But what is y squared? Well, we know what y is now. Y is this, right? So let's do a substitution. This becomes negative x squared over x minus 1 squared over x squared.
Oh, so then they cancel out.
So this is over 1. It reciprocates. They divide away. And I'm left with negative 1 over x minus 1 squared. So again, is implicit differentiation a new differentiation? No. No, it's not new. It's not new, McKenna, because I got the same thing when I differentiated implicitly that I did when I differentiated explicitly. It's not a new differentiation. The only difference between implicit and explicit is that when you implicitly differentiate, you are admitting that you don't know what y is as a function of x. You don't know the analytic form of y. You don't know the equation for y as a function of x. That's the only difference. Okay? All right, let's take an example where we can't know, by the way. Here's an example where we can't know y as a function of x. X squared y plus 3xy cubed minus x equals 3. Y cannot be solved with any of the techniques that we know. Yeah, you've got a cube here and a 1 or y to the first here. So there's nothing that we can do with the techniques that we've learned from algebra and precalculus at this stage to actually solve for y as a function of x. Well, what does that mean about the derivative? Well, it means that only implicit differentiation is possible.
So just
Do the derivative implicitly, because the explicit is not known. So we begin. This is a product.
first
So x squared dy dx plus 2xy. This is another product. 9xy squared dy dx plus 3y cubed minus 1 equals 0. Okay, do you see how I used my product rule? I had to use the product rule here and here. First times the derivative of the second, so that's x squared dy dx. Plus second times the derivative of the first, so that's 2xy. Then I had to do it again. First times the derivative of the second. So the derivative of this is 3y squared dy dx, but the 3 multiplies by this 3, giving me 9. So I get 9xy squared dy dx plus second times the derivative of the first, but the derivative of 3x is 3, so I'm just left with 3y cubed. Minus 1, the derivative of that, equals 0. Now let's solve for dy dx. So what we do is we gather all of our like terms, x squared plus 9xy dy dx, and we subtract everything that's not a dy dx to the other side. So this becomes 1 minus 3y cubed minus 2xy, and so the final answer, dy dx implicitly, is 1 minus 3y cubed minus 2xy all over x squared plus 9xy. That is the answer. Now, do I know what y is as a function of x? I still don't know.
Because you can't solve for it.
Can't solve for y. I can't substitute things back in to get an equation that just has x's in it. Okay? But the reality is that this is no less of a good answer than the other one. Because in the real world, you don't really know what the function is. You have data. So you can still plug in ordered pairs and figure out what the slope is from your data. And when I say data, all I mean is massive XY tables. That's all I mean by data. Okay? All right, let me just make a quick comment here. The way that you would do 16, by the way, is you could use the quotient rule, but there's a much easier way, Carrie. To do this implicitly, it would be way easier to just multiply both sides by x minus y and then distribute the x squared into the x minus y and then start to do implicit differentiation. That would be the way easier way to do it. Okay, right here. Find the slope of the tangent line to the curve at the given points in two ways. First, by solving for y in terms of x and differentiating, and then by implicit differentiation. So let's take this first equation, x squared plus y squared equals 1, which, by the way, is the equation of what? That's the equation of a unit circle.
Oh yeah.
Okay? And so x squared plus y squared equals 1. Let's solve for y as a function of x. Would you agree with me that y is equal to plus and minus square root of 1 minus x squared? Okay. So that means that dy dx would equal plus and minus 1/2 square root of 1 minus x squared times negative 2x. Reduce the 2's, so plus and minus x over the square root of 1 minus x squared becomes the derivative. All right, now let's do this implicitly. So David, what's the first part if we're going to do this implicitly?
2x.
Plus, and then Carrie, what does this become?
D over dx.
dy dx equals 0. Now solve for dy dx. dy dx equals negative x over y when you solve it. Now let's go back. Here's an ordered pair, David. 1 over square root of 2, 1 over square root of 2. So now we're going to find the slope of the tangent line. So what I do is I put 1 negative 1 over square root of 2, 1 over square root of 2. Negative 1 is the slope of the tangent line.
Why did you do D1?
Whoops. Just to keep you on your toes. This is the slope of the tangent line at the point 1 over square root of 2, comma, 1 over square root of 2. Okay? If we wanted to get a tangent line equation out of this, y minus 1 over square root of 2 equals negative 1 times x minus 1 over square root of 2. That would give me the equation, right? All right, now let's do the same thing here, except notice, McKenna, this only has x's. So all I have to do is plug in the x value of the ordered pair. So I get plus and minus 1 over square root of 2. Square root of 1 minus 1 over square root of 2 squared. Now what's 1 over square root of 2 squared? 1/2. What's 1 minus a half? 1/2. And then you take the square root and you get 1 over square root of 2 again. So it's 1 over square root of 2 over 1 over square root of 2, which is plus or minus 1 when it's all said and done. Now the reason, David, why we're getting a plus and minus 1 here is because this technically is not a function anymore. This is two different equations, a plus root and a minus root. So we're going to get both slopes here. But if I go to this ordered pair here, McKenna, 1 over square root of 2, negative 1 over square root of 2, and if I plug that in here, then that gives me the positive 1 as a slope when I plug that in here. Some of these things, Carrie, look really weird. For example, xy equals cosine of y. Looks like that. So what we're dealing with here is not even a function.
How do you solve for that?
How do you solve for that one? You mean, how do you differentiate? Well, here's an ordered pair. Would you agree that that's an ordered pair on the curve? Could you create a tangent line to that ordered pair? Absolutely. And what that means then, David, is that since this is nice and continuous, this is differentiable still, even though it's not a function. It's still differentiable. And what that means is that expands our understanding. Before, we've only been finding derivatives of functions. But now, with implicit differentiation, we can find derivatives of relations, which are not necessarily functions. They don't pass the vertical line test. Here's another ordered pair, x comma y. Does a tangent line exist here? Absolutely. And since the tangent line exists, and it's nice and smooth, we know that it's differentiable. So here's where our expanding gets a little bit broader than it was before. Before, Carrie, we were only differentiating functions, things that pass the vertical line test. Now we're even more powerful. We can now differentiate what's called relations, and a relation doesn't have to pass the vertical line test. Different, huh? All right, some of these things look really weird, really weird. For example, let's take sine of x squared y squared equals x. Let's expand that out. Some of these curves are very beautiful.
It's really artistic.
Yeah. You'd never expect it to look like that unless you started plotting points in. But right here, I zoomed in. If I put a point here where my cursor is, that's an ordered pair on the curve, right?
Okay.
Is there a tangent line to that point? Absolutely. It is differentiable. Now, there are places, McKenna, as you go up in the curve, where it gets really, really, really thin, almost to the point of a line. And these places right here, these little points, these are points where it's really not differentiable. It's kind of like that cusp that we had before, when we had something like this. But at least down here, the curve is nice and smooth. So these points are differentiable. Let's graph another one. Oh, what does, I wonder what y plus sine y equals x looks like. Let's try that one. It's almost like the line y equals x, except it's picked up some waviness. If you drop the sine y, if you eliminate it, then you have y equals x, right? You have got a straight line. But plop in a sine of y, and it gets wiggly. Now, the moment I say 3, it gets even wigglier as it goes straight up. Let's see, there's another one in here that's pretty interesting. Yeah, I've got to do this one. This is the popular, what's it called again? I want to say Lemonesque. I might be wrong on that. The Folium of Descartes. There we go. The Folium of Descartes. X cubed plus y cubed equals 3xy. This is the Folium of Descartes. What you're seeing are all the ordered pairs that satisfy the equation x cubed plus y cubed equals 3xy. Now, as you go out to negative infinity, it approaches, it gets straighter and straighter and straighter, but somewhere, for some reason, Carrie, around the origin, it does this loop-de-loop thing, and then goes back to approaching a straight line.
Weird.
It is weird. There is one place, though. There is one place on this curve where it's not differentiable.
Is that the 0?
0, 0. There's an infinite tangent line here. Several. There's several tangent lines. So that's the one place where it's non-differentiable. Other than that, there are tangent lines that exist to the curve. Yeah, I've heard about the update.
No, I know. Someone that has already put 7.45 on the computer,
Uh-huh.
how do I divert it back as television?
Okay. So, we're a little bit behind, so what you're going to do for me today is not the Friday homework. Not the Friday homework. It's the Thursday. It's the 1 through 26 that you're going to do for me. And let's just look at this homework real quick. Notice right here, David, in numbers 1 through 8, it's simply saying find dy dx. This is explicitly,
Okay.
because we know y as a function of x.
Okay. So you just differentiate.
That's exactly right. You good old derivative like normal. Because again, I'm going to say it again, I'm going to harp on this. Implicit differentiation is not a new differentiation. Okay. Numbers 9, however, 9 and 10, this is where we finally get to do a little bit of implicit differentiation. And then 11 through 16, more implicit, actually goes through 20. And then when you get to 21, this is where you're going to find the second derivative of y with respect to x the second time, implicitly. So you've got to do 2 derivatives. Yes. And what you'll have to do is once you find d2y dx2, you'll have an equation where you have to substitute in what you found for dy dx.
And then,
So let's just do, well, we've only got 2 minutes, I don't know, but I'll try it. Let's do 21. 3x squared minus 4y squared equals 7. 3x squared minus 4y squared equals 7. The first derivative would be 6x minus 8y dy dx equals 0. The next derivative would be 6 minus 8y dy d2y dx2 minus 8 dy dx squared equals 0. Okay, differentiate this again. Derivative of 6x is 6. Now you have to use what rule here? So first times the derivative of the second. Well, what's the derivative of dy dx? d2y dx2. Plus the second times the derivative of the first, but the derivative of this is negative 8 dy dx.
That's minus
So you've got dy dx times dy dx, so there's dy dx squared. Now what we have to do is we have to solve this for dy dx. So dy dx here is equal to 6x over 8y, which is equal to 3x over 4y. And now we can substitute that in here. So this is 6 minus 8y, 3, not here, I'm sorry, that's still d2. d2y over dx2 minus 8, there we go, 3x over 4y squared equals 0.
and then we can solve
And now you can solve for d2y dx2.
Okay, so fine.
So the final answer is this becomes 9x squared over 16y squared. But that's times negative 8. So this becomes negative 9x squared over 2y squared. This becomes negative 8y d2y dx2. And that's a 6 equals 0. So add this over here, subtract the 6, divide by negative 8. And which you can do that. Divide by negative 8y. There we go. And that, as we say, is that. God bless you wherever you are today.